Welcome to my video on nuclear radioactive half-life. Half-life is the term, if you've ever played the game, just cut the Half-Life 3 jokes right now, because I swear to God, if I see one in the comments, I'm going to block you, because I just want Half-Life 3 to come out. But anyway, half-life is also a physics term that means how long it takes for, let's say, 30 grams of this uranium. Once it reaches a certain time, half of it will be gone. So what I'm essentially saying is we've got 30 grams of uranium-236. This, by the way, does go through alpha, I believe. I don't know. So basically that, after it reaches a certain time, 30 grams will become 15 grams. So half-life is decay by half. But here's where it gets even better. If you're 15 grams, once it reaches another half-life, there'll only be 7.5 grams left. So it decays by half after each time. That's all half-life is. Now, there is a formula for half-life, however. We say the number of substance remaining is equal to the initial amount times half to the power of the number of half-lives. So every isotope has a specific half-life. I'm actually just going to write that up here. Small text so you can look at it's up there. Okay, so it's up there now. So half-life, what we're saying is every isotope has an individual half-life. You can only remember them or Google them as with what type of decay goes to different elements. So I have my handy-dandy Wikipedia list which tells me all the decays. So what I'm going to do now, we're essentially going to make a question. So I'm just going to pick a random element. I'm going to go with, this one has a decent amount, like a year's half-life, like a long half-life. Let's do carbon-14. I'm going to try to get this one on 10 minutes. Carbon-14 has, this is the symbol for half-life, by the way. We can just do that. T half equals 5,000. So we have a half-life of 5,701 years for carbon-14. Then essentially what we do is the way we do this equation, so we know this is the certain time. Google, Wikipedia, whatever will tell you the half-life. Or you can only remember them. There's no way of telling it. So basically, this is our time of half-life. So if you've got a question, say, I don't know, carbon-14's half-life was 5,701 years, yeah? So what we do is, let's say, I don't know, let's put it into 3 half-lives. I'm going to say, grab my calculator and do this. 5,701 times 3. So 3 half-lives. Hell, yep, that'll do. 3 half-lives of this is going to be 17,103 years. Because that's that times 3, which gives us 3 of these half-lives. So all it is how long it takes to decay by half after each time it reaches this time. So now we want to, okay, well if I had, say, let's go a really low number just for fun. Let's go 3.5 grams, so you can't calculate it easily, like 10, 5, 2.5, 1.25. That's a bit easier. Let's go a really hard number. Well, I mean, I could tell you the second one will be 1.25. That's about best. So yeah. No, that actually would be 2.5. 1.75, whatever. Okay, so now what we do is plug it into the formula. And plug it into our formula. So this I'm going to write all the constant, what all these letters mean. So N is the number remaining. So the number of substance remaining is N. Initial amount, so how much of it we've got. It can be in any unit. Grams, kilograms, atoms. I don't know how many nanograms have I got. It can be in whatever you want. Okay, so you should just write these two down. Then N is the number of half-lives. I'm just going to write this out because I'm on a very small whiteboard, that's all. Half-lives. Number of half-lives. So we know our formula, so if we We want to know how much after 3 half-lives, which is 1 half-life times 3 gives us 3 half-lives. So that's the actual, I believe that's the actual half-life for it. Okay, so what I'm going to do, we've got 3.5 gram of carbon-14, half-life is 5,701 years. Some take like nanoseconds to decay, but some of these radioisotopes or isotopes take like a long time. Uranium-238, when we looked at an alpha decay, takes 4.5 billion years just to decay by half. You'll be dead by the time it even got a little bit of decay, a little bit of alpha particles, and a bit of thorium-234 out of it. So now what we're going to do is this. We're going to plug in our formula. So we know we want to work out how much we've got left after 3 half-lives. We're going to number of substance that we have left is equal to our initial substance, 3.5 grams. Then we go times half to the power of our 3 half-lives. That times 3 gives us 3 half-lives, which is 17,103 years. So now we measure this in whatever substance you started with, so grams atoms. So this will be in grams in this case. So now I've got my calculator here, and I'm essentially just going to show you some calculations. Oh, this is very awkward with the camera, but that'll be fine. Okay, so we've got 3.5 times a half to the power of 3. We're going to have that much left after 3 half-lives. So we're going to have 0.4375 grams left. So what you do, if you were to times that by 3, you should get 3.5. Okay, oh, I was actually kind of wrong there. Ignore what I just did. That was silly. Anyway, now for a question. So you all know half-life is how long in time it takes for an isotope to decay by half. It's in a half-life. Think of it that way. So that's my definition. To decay by half. Yeah, that's my definition. Good. Okay, definition now. I'm going to write a couple questions, and hopefully we'll get this under 10 minutes. Alright, these questions might take a while, so we can make it, I'll do 11 minutes, 10 minutes, 30 minutes. Question 1. If uranium-238's half-life, which actually is 4.5 billion years, so no, that's that. And essentially what I want you guys to do, if that's uranium-238's half-life, and if I had a 30 gram, actually I'm not going to write this question. So what I'm saying, if uranium-238 has a half-life of 4.5 billion years, how much of a 30 gram sample would remain after 9 billion years? Go through the question. You don't even have to use me. If you want to, go online and watch another video if you hate me. But yeah, go through this. I'll come back in a sec. Pause the video, go through it. Alright, assuming you guys will pause. So what's it asking? So essentially we know, stop rubbing these out. We know uranium-238's half-life is 4.5 billion years. Alright, we know that. So now we know our half-life. We're told we have a 30 gram sample. So we got a few facts from this equation, from this question anyway. Half-life is 4.5 billion years. We have sample. Actually, no, I'm going to write that as this. Our sample size, our initial amount, is 30 grams. We've been told that the time it takes, that it wants, is 9 billion years. And that was it, wasn't it? Let me read the question again. Yep, that's it. Okay, so all it wants, essentially, we plug it into our formula. N, substance equals the initial amount times half to the power of number of half-lives. How many half-lives do we have here? Well, 4.5 billion years and 9 billion years. 4.5 plus another 4.5 plus... So that plus another 4.5 gives us 2 half-lives of 9 billion years. So we've got 2 of these times. That times 2 will give you that. So that means it's 2 half-lives. And we've got 30 grams to start off with. So 30 times half to the power of 2. So now we actually do the maths for this. All we've got to do is this. And that will give you, the answer should be 7.5 grams left. There should only be 7.5 grams left of uranium-238. Alright, I really want to do another question, but I know I'm running over time. Well, worst case scenario, depending on the time, I might be able to get the rest of this course done. That's my personal shit. I need to worry about getting this done. Right, so now we've got iodine. Okay. Iodine 129. And that has a half-life of, a bit smaller, but still not greatly, 15.7 million years. 15.7 million years. So 15,700,000 years. Now, we've been told that we have 8 billion atoms. So this time it's not in grams, it's in atoms. So basically, this is the question. Alright, you guys, I'm going to read the question and jot it down if you want to. I'm just getting the solution ready. If iodine 129 has a half-life of 15.7 million years, how much would remain of an 8 billion atom sample after 7.85 times 10 to the power of 7 years? So in other words, 78.5 million years. Okay, I'm hoping you guys jot that down and pause the video and work it yourself. You're not going to learn much if you don't do it by yourself. This is just the starting factor. You guys need to do the work in order to get this done. So we've been told iodine 129 half-life equals 1.57 times 10 to the power of 7 years, right? So we've been told. So the next step, all we have to do, we've been told out, we've got 8 billion atoms. I'm guessing you guys are all aware of scientific notation. If you're doing this level of physics and chem, you should know what scientific notation is by now. That's basically 8, or you guys actually should know that. I'm not even going to explain it. If you're confused, go Google it yourself, because you really should know scientific notation if you're doing this by now. Okay, I'll probably go through that if you want to do in the foundation chem one. Solve for the mass defect. Oh no, sorry, that's one of my other exercises. Apologies, I'm not thinking of them. I've been told our time it took for the sample was 7.85 times 10 to the 7 years. Okay, so now, what's the time? I don't know. Anyway, so what we need to do is this. So plugging into our formula. Our new amount is going to equal our initial amount times half to the power of half-lives. But you might be going, how do I know how many half-lives that is? If you want to actually, if you've got a big number like this, and you can't just go like 4.5 billion, 9 billion, no, it's 2. What you can do is this. Half-life equals, in our case, it's the time, number of half-lives equals the time over the standard half-life over how many times it occurs. So how many, actually, hang on now. Bear with me. All we do is we take this number. Sorry guys, I'm really trying to rush. I might actually redo this video if you guys want. If you guys comment redo it, I will redo this video. 1.57 times 10 to the 7. This is basically going to give us this number divided by this number. It's going to give us how many half-lives we have. And I'm telling you now, from memory, I made this question, so I know it should be 5. Just double check. And it is 5, yes. So we have 5 half-lives. So we know 8 billion atoms. And we've got 5 half-lives. Got 5 half-lives. Right. So now we just plug in our formula. 8 billion atoms. And remember, it's going to give us it in whatever unit we use here will be the unit we get. So how many atoms are we going to have left in this nucleus of I don't want to know what the fuck it was. I'm actually starting to lose concentration. So it's going to be that times half to the power of 5. I'm just going to get some real quick because now we're nearly at the 20-minute mark. 8 times 10 to the power of 9. I'm actually going to use brackets. It's not calculator, what's the glitch? What's your little shit when it comes to this sort of thing? It's going to be about 1, 2, 3, 250 million. It's going to give you 250 mil. So that'll be this. It's the power of 8. So yeah, and that's half-life in a nutshell.